Okay, as Fiona said, yesterday we covered the fundamentals, I guess you could call them, like the foundation of transmission lines, and we went up to wave propagation. So I remember yesterday I said that for this topic, it's just in one situation mostly. So if I could just go through an example that just comes after wave propagation. Okay. The general equation that we looked at Jana. Then going through section 2.5 on wave propagation will also be a breeze. If that equation was well understood, section 2.5 is well understood. Okay, so I will be taking us through the example on page 77. Let me present. Someone tell me when you can see my screen.
We can.
So this number 3, a coaxial cable operating is equals to 234 nanohenries per meter, C is equal to 93.5 picofarad per meter, R is equals to 0.568 ohms per meter, and G is equals to 0. It's using me. I'm sorry. The phase shift coefficient and the output of omega t minus pi over 3. So, yeah. Can you guys see this handwritten?
Yes.
Anybody? Okay, so okay, what I advise for figures in assignments, because even myself, also doing some of these questions, I noticed that I was, yeah.
Could you please do
like that?
Yeah.
Is it good? Is it good now? You to write all of your for ease of consistency, because you might miss a micro, you might treat the first thing is to find the characteristic impedance. So what you can see from here is that if G is equals to 0 and R is equals to 0.568, okay, maybe the R is not very important, but the G is equals to 0. So characteristic impedance will be very dependent on these primary line constants. So if I can just go back to this class, these class notes, when you go through the notes, you will see that if we go back to here, we come here, you will see that there are a lot of formulas that are being used for Nini to find this characteristic impedance. So depending on the situation in which you're in and the variables which you have been given, that's how you'll pick for yourself whether root R over G is the best one to use, whether this will be the best one, whether you're going to be using this is equals to the root of L over C. This is what it's just a matter of knowing which formula to apply in which situation. So for example, in this one, you'll use this. In another situation, you might have a very low frequency where you'll end up using Z naught is equals to the root of R over G or something like that. So yeah, when you use Z naught is equals to L over C, the root of L over C, and then you punch this into your calculator, you get 50.02673, which approximates to 50 ohms. Questions? Any question?
No questions.
Okay, I assume that. So again, even with the attenuation coefficient, you look at what you have, what you can use in this situation. So if I go back to these notes and just go to this attenuation, yeah. So here, if you use a high frequency approximation, mostly because G is equal to 0, if we, I can confirm that for you. The math of how this becomes this is not that important. As long as,
Oh, Gishiru, there's a question.
like for example here, we have alpha, yeah.
What qualifies as very high frequency?
Okay, let me. What qualifies as very high frequency? What qualifies as very high frequency? I don't have G. We don't have G conductance. And if you look at every formula that has to do with obtaining the characteristic impedance Z naught, it's all of it is a root of something. Now, if we don't have G, and then we try and do a division between one number that has a real part and an imaginary part. Okay, I did this on the calculator. I tried using the other formulas that have both, that have R, L, and C, and G, and you end up getting an imaginary number as your result, and you can't find the root of an imaginary number. I was getting math errors. So I assume that for characteristic impedance, you just do what's going to give you a real number before you do the square root. I guess it's a rule of thumb. You can say it's a rule of thumb. I guess it all depends on what you've been given, the primary line constants which you've been given in the question. And that depends on the question. Does that answer you? Liz? Oh yeah, also the RF range is from 3 kilohertz to about 300 gigahertz. So in that ballpark, 3 kilohertz to 300 gigahertz, you can decide which, when you see a number, you see for yourself, is this formulas during the exam. So yeah, okay, yeah, I'll continue from there. Will be equal to R over twice Z, which is R over 50 times 2, which you'll get. And then again for the phase shift coefficient, okay, this formula might look a bit terrifying. Back up what it is that I did up there. This, you see this curly brace, everything, this curly brace thing, this 1 plus an eighth into R of omega L minus G of omega C squared. When you do that math, including the whole R thing, this bracket equates to 1.000 something. So that approximates to 1. So again, just to back up what I had said earlier about these two. Yeah, if we take the very high frequency approximation and leave this part out, if you leave these curly braces out, to be very much different from what I've done here. Okay, if you use this long thing, G is equal to 0, omega is equal to 2 pi f, and then you plug in all the values you've been given, you're going to end up with 0.29395 radians per meter. And if you just do beta is equals to omega times the root of LC, so you see the difference is on the 4th decimal place. It's basically negligible. So this is just like, I guess, proof of what I'd said earlier. You can take it as some sort of proof. Are we good until there?
Yes.
Abby, have any questions?
Yes.
Yeah, there's a. Oh,
Wait, no questions.
sawa
No.
sawa. Okay. We're back to part D. So part D reads, find the output of a 100-meter line if the input is 50 cos omega t minus pi over 3 volts. So from what we saw just now, the voltage at any point in the line will take this form. Its magnitude will take the form And the phase shift will take this form, the cosine minus phi, not minus 0, Jesus. Okay. So this minus phi comes in. Let me just pull up the class text so you can see for yourselves. It's here. Come up. These come up from what we did, what we saw Jana. And then also, I guess this paragraph is worth taking into account. The actual sinusoidal current in the line is determined by multiplying the time component and then taking the real or imaginary part depending on the form of the source waveform. So if you have the actual current I, if the source takes us as sine waveform, you'll take the imaginary part of I e j omega t, where this I is equal to this I is equal to this over here, up here. And if it takes a cosine waveform, you will take the real part of this. And this is from Euler's formula, which says that e to the power j omega t is equal to the cosine of omega t plus j sine omega t. So since the j precedes the sine part, you'll take the imaginary, and the cosine does not have a j attached to it, so you'll just take it as a real part. So here, this is where the phi comes from. Since for a matched to infinite line, that z naught is equal to the magnitude of z naught divided by here minus phi with the assumption of capacitive impedance as seen in practice. I guess the as seen in practice is like from experience with people who work with these things. So yeah. From here, you'll find that this with V should be equal to V is equals to Vs E minus alpha x. If you take the cosine part, it will be Vs E minus alpha x cosine of phi comes from. Are there any questions there?
No.
Yes, sour. So to find the magnitude of the output voltage, it will be 50 times e to the power of the attenuation that we got earlier. The attenuation we got earlier was in Nepers per meter. So if you want V at the end, you have to multiply it by the length. You have to multiply the attenuation by the length of the line. So it will be 0.00568 times 100. So you get 0.3. Also, in his notes, he's given his answer for phase shift coefficient as 0.2953. And well, we got 0.29395. I honestly have no idea where he got 0.2953. We tried to get it, we could not get it. So we worked with what we have. So now, in this question, our phi is pi over 3. So it will take the form omega t minus beta x. This is beta times x, because beta was also in per meter. So you need to multiply by the length of the line minus pi over 3. So you get cos of omega t minus 30.4422. So if you look at this figure, 30.4422, that's a hell of a lot of radians. So this clearly is more than one revolution. So if you want to find how many, divide it by the radians that make up one full revolution. So you find that these 30 point whatever give you 4.845 revolutions. So to find the displaced angle, the angle that is less than 2 pi, you just remove the one that's not complete, which is 0.845 over revolution. So to find what that revolution is in radians, you'll multiply it again by 2 pi, and then you get 5.3095. This I've made a mistake here. I will correct it before I send it to the group. So you get cosine of omega t minus 5.3095. And from trigonometry, if you plot a circle on the Cartesian coordinates, if you go a certain angle in the negative direction, it's equivalent to going the whole 360 minus that negative angle to get the angle you're going to go in the positive direction. I hope that was not confusing. And well,
Repeat.
I'm not Travis. I don't have very nice interactive applications. I'm sorry?
Oh, someone asked you to repeat kindly.
Was there a question? Okay, let me see if I can explain this slowly. If you draw the Cartesian coordinates, like the plus thing, and then you draw like a full circle, that moving in the clockwise direction is negative and moving in the anti-clockwise direction is positive, right? So, so
Yeah.
if I move so many degrees in the negative direction, it's equivalent to me moving. If I move so many degrees in the clockwise direction, it's the same as me moving from the total number of degrees up to that point in the opposite direction. The opposite direction, negative direction. You get? Do you
There was a point
understand?
in Komohang, I think my wife was, but what on text on it.
Plus 0.9737. This is not omega t minus. That's the mistake I made. I will correct it. I'll correct that. Sorry, this is omega t plus 0.9737.
Okay, Gisheru. There was a point when you're explaining you were cut out, and
So
we didn't quite get your explanation. Is it possible for you to repeat?
Where
exactly did I get cut out? At what point? Can you guys hear me? Am I still here? Can you hear?
Yeah, we can hear you.
Oh, okay.
Yes.
Where did I get cut out?
Just start from the top, please.
Okay, so part D. Okay, so part D. Did you see how I end the part where I was explaining how it becomes the cosine of omega t minus beta x minus phi? Did you at least get that part?
Yes.
Okay, sawa sawa. Okay, so I was saying that, so the magnitude of the output voltage will be the source voltage times E power minus alpha x, which is 50, times E power minus 0.568, because this is alpha x, and you get 28.33. Now I'm guessing this is the confusing part. Explain. If a field has a perimeter of 200 meters and you cover a total distance of 1100 meters, that means you've like gone around the field 5.5 times. Sindio? So, like in this case, the perimeter of the field is now minus 29.395 minus pi over 3. That's the perimeter of the field. So if you've gone around the field, if you've gone 1100 meters and someone wants to know how many laps you've done, you're going to take the total distance you've covered divided by the perimeter of the field divided by 1 lap. And that's how you get 5.5. So this, the perimeter of the field is 2 pi, and the distance you have run around the field is this 30.4422. Are we good until there? Are you fine until there?
Yes.
Okay, so if I do the distance I have run divided by the length of a lap, you're going to get, well, 5.5 in my example. But here now, if you do 30.4422 divided by 2 pi, you're going to get 4.85. So if I want to know how much. I have 5 complete laps and 1 incomplete lap. Sindio. So if I want to know the length of that incomplete lap, I will take its fraction of a whole lap and multiply it by the length of a lap. So you'll do 0.5 times 200, which is 100, which is the same thing I've done here. I have removed 4 from 4.845 and then multiplied the fraction of the incomplete lap by the perimeter of that field, which is 2 pi, and then you get 5.3095. That is how much that's how much in the incomplete lap that I have done. Are we good until there?
Yes.
Yes, we are.
Anyone? Sawa. So if I decide to remove those complete laps, and you want to see how far I have gone in the incomplete lap, it's this 5.3095. Now let's say I was running the lap anti-clockwise. I was running the lap clockwise. And I ran up to the point 5.3095. So if I went back to the beginning and I ran in the I can get the distance of that anti-clockwise movement from doing the length of a whole lap minus the 5.3095. You get that? Are we good until there? Hello?
Yes.
Okay, so if the clockwise movement was negative, then the anti-clockwise movement would be positive. So if you do the perimeter, the 3095 in the negative direction, it's like going 0.9737 distance in the positive direction, which will make this plus. Again, this is a mistake. This will be plus 0. Do we get that?
Wait, Gisheru, you are breaking. Just when you said something about the negative direction, you started breaking.
At what? Okay, I'm sorry. Today the internet is being very, very unreliable.
It's okay.
Okay, how about if I'm starting at a point X and I'm moving in the clockwise, I'm running around this field in the clockwise direction. And my distance, I'm going in the wrong direction. So I'm covering negative distance. So if I run around this field up to a point minus I cover 5.3095 radians, but I'm moving in the negative direction. So it's like I've gone minus 5.3095 radian. Have they broken at any point? Hello?
Oh,
Hello?
hi, you can continue, sorry.
So, so it's like I've gone this distance away from the starting point, and then I've stopped at a point minus 5.3095. So if there's someone at the starting point who wants to come to the point I am at, but since they are smart, they move in the positive direction. The positive direction being the anti-clockwise direction. They will cover the whole thing, the whole lap, minus the distance I have covered in the wrong direction. Because they won't have to cover it. You get. Are we good? Anybody? Are we good?
There's a question, but won't the positive direction be short, be shorter?
I mean, yes, I am assuming that 0.9737 is smaller than 5.3095.
Oh wait, sorry, longer.
Is it not?
Sorry, longer.
Fiona has Sketch, drives this very nice app. How about she shows you, graphically, diagrammatically, how this thing works? Sawa.
Sawa.
So,
It is.
Hi, mnanisikia? Mnanisikia?
Yes.
Hello?
Yeah.
Okay. So this is what Kisharu is trying to say. He's trying to say, I hope and he was very good at this. So let's say this is a circle, right? So, and this is that kind of circle. Sindio, for the degrees thing like that. Okay. So to sum E2, it was negative 5.31 radians. That's what you got. Sindio. And when you convert this radians to degrees, it becomes negative 304 degrees. So, and how do we usually move? See, when we have the circle thing, we usually move like this. Sindio, that's our positive direction. I need someone to put their mic on so that I know we are going together. So that's a positive direction. Sindio. But then this is negative 304 degrees. So I hope I am not wrong, but I think it will go like this. Same some distance like this. Same on negative 304 degrees. What Kisheru is trying to say, he's trying to say that distance going like that is the same as that angle is the same as this in the positive direction. Yani that negative angle in that negative thing, that negative arrow angle is the same as the positive angle for the green. So this green arrow, 360 minus 304 degrees, you get what? You get 55.79 degrees. So this is 57.9 degrees. And this other one is negative 304 degrees. So he's just saying that. That's what he's saying in many words. But then now you have to like this degrees you convert, when you convert these degrees to radians, it becomes negative, it becomes positive 0.973, that thing, because now this positive side is equal to this negative side. Mumeelewa?
Yes, it's been understood.
Okay. Stop. Wait. You share room now, you can continue.
Okay, thank you. Thanks a lot. Say, I'll talk a little bit on termination of Nigel still has to present. So what I will do is I will just take us through the second question, that a very small question that she was supposed to take us through. We'll try to do that as quickly as we can, and then we give Nigel the floor. So.
So,
Okay.
okay.
Tell me when you can see my screen.
We can see your screen.
We can see it.
In your
Tunaona.
so can I zoom this? Yes. Okay. So the question, this question is on page 182. I think, yeah, page 182. Question 2. Let me just open it. No, clearly it's not there.
Umepita, ni page 190.
Okay, yeah. Right, but so yeah, this. So we did part A of this question. So 100 ohm lossless line has a node separated from the next antinode by 3.7 line wavelength, the line dielectrics relative permittivity, the line phase shift coefficient, the line phase velocity, and the primary line constants. We have this sentence has a node separated from the next antinode by 3.75 millimeters. This was explained in the section on termination of transmission lines, which I wish I would have been able to. It's not difficult. If I could understand it, you guys can in probably a shorter time. So yeah, basically what it says is that when you have the incident and the reflected waveforms, let me just here. So when you have, I will use this to quickly explain. When you have the incident wave and the reflected wave, as the way they're in part B, this is now what we're calling a node. So if you imagine this line at the top going, if you imagine that the whole distance, this whole distance going around like this would be lambda, would be one wavelength. Yeah. And if this one at the top is going in the clockwise direction, and this one at the bottom is going in the anti-clockwise direction, because one line at the top will travel a quarter of the whole circumference, and the line at the bottom will also travel a quarter of the whole circumference. So on each wave, it will take a quarter of lambda to go from B to C, to go from node to antinode. Is that understood? Hello? Have I broken again?
Oh, no, we
We
can
can
hear
hear
you.
you.
And that's understood.
We can hear you.
Mko sawa?
Yes.
Okay. So knowledge and applying it to part A, since we've been given the node and the nodes separation, we will just multiply what we have by lambda over 4. So we'll give 15 millimeters in line wavelength. To the next question, if you missed that, or if you want to go through it again, just go for the recording. It's posted on the Telegram group. So you have lambda is equals to VP over F. You have all of this, and when you plug all of this into, when you plug what we've been given into this, you'll get 4. For part C was also covered yesterday. Beta is equal to 2 pi over lambda, which is 2 pi radians over 0.015 meters. So you get 418.88 radians per meter. It's a lot. But yeah, you get that since 2 pi is already in radians and lambda is already in meters, you won't have to divide by the length of the line because it's already in radians per meter. So for the phase velocity, I think this was also covered yesterday. We'll get omega, which is 2 pi f, so 2 pi times 10 gigahertz divided by the amount of radians that we just got, which will give you 1.5 times 10 to the power. Good until there.
Yes, yes.
Okay, good. Are you, did I break? Okay. The part E for the primary constants. C, in the question, we're told that the line is lossless, which means that the attenuation is 0. And the attenuation will come from the real parts of the propagation coefficient. The real parts being R and G. So if or G or both are equal to 0, and since we've not been given R or G, we will assume from line being lossless that R is equals to G is equals to 0, or R is equals to G is equals to negligible or something, just to go with 0. So the primary line in play in this question are just L and C. And we know that beta is equals to omega times the root of LC, which I looked at in the previous question. And we also know that Z naught is equals to the root of L over C, which was looked at again in the previous question. So when you do the math, all you have to do is square, like here, just square both sides, take something to the other side. Even here, square both sides, take something to the other side. So if you do this, the root of LC is, well, that. This is just simple math. So you get 100 squared C times C is equal to this. So you get C squared is equal to, well, this divided by 100 squared, which is 66.7 picofarad. You find L from 100 squared C. You get L is equal to 6.7 nanohenries per meter. So yeah, I think that's the last part of that question. Yeah, yes, it's the last part. Okay, so I guess with that I'm done. I'm done with what I wanted to present, and Fiona can take over from here.
Okay, thank you.
Were there any questions? Were there any questions? Did I break?
Thank you, Kishiru. Once it's on, please let me know. So, question.
It's on.
Okay, so I wanted to do question 91. A lossless air dielectric, 54 ohms, 2.25 meter long line operating at 150 megahertz is driven by a source dot and is terminated in an impedance ZL, which is equal to 115 minus J 75 ohms. Determine all those things. So we won't go into deriving these formulas because they're pretty much straightforward. Now part one, we were to find what the, okay, so what do we have? We have the frequency 150 megahertz. So this tells us we are operating in the range of, can you guys see? Can you guys see?
Yes. Please could you zoom in just a bit if we can see.
Is that okay? Okay, so the
Yes.
frequency is 150 megahertz. So, and we are being told the source voltage is that, and the line length is 2.25 meters. And when you're told that something is lossless, when a transmission line is lossless, it means attenuation is equal to 0. And when attenuation is equal to 0, that means when attenuation is equal to 0, that means R is equal to G is equal to 0. So our characteristic impedance is 54 ohms, and ZL is 115 minus J, 75 ohms. Okay, so so to find the wavelength, we'll say phase velocity divided by frequency, but phase velocity is speed of light divided by the root of the dielectric times frequency. And we were told that's an air dielectric, so the relative permittivity is 1. So when you input those values there, you get your wavelength as 2 meters. So now we go to length in wavelength. So when you ask the length in wavelengths, we were already told our length is 2.25 meters. So what they just want us to convert these 2.25 meters to wavelengths. And we know what for and we know one wavelength, sorry. And we know one wavelength is what? Is 2 meters. So what about 2.25 meters? So you do that and you find 1.125 meters. Then you do the phase shift coefficient. The phase shift coefficient is beta, right? So you divide by the lambda. So the real thing comes now here. Our primary line constants, Gishiro has taken us through that. When you told attenuation is equal to 0, you know that R and G are also equal to 0. So we found two primary line constants, that's R and G. If there are any questions, please someone shout out because I'm on presentation mode, I can't see. So our characteristic impedance is equal to root of L over C.
And
that's
the question brought up.
Yes? Yes?
Yeah, I said there were no questions.
Oh, okay.
There are no questions.
Thank you. I think I'm lagging. So Z0 is a characteristic impedance for high frequencies. We know it's root L over C. This is high frequency, 150 megahertz. So is equal to 54 ohms. And then we have that, so we form our second equation using the phase shift coefficient, which this is also a condition for high frequencies, where the phase shift coefficient is equal to omega root LC. So that's our second equation. When you do this first equation, when you do this one and this one, when you do those two, you will get and make LC simultaneous equations. I think that you guys can. We will find L is equal to 0.18 microhenry at 61.73 picofarads per meter. And this is per meter. And R and G are equal to 0. I don't want to go into that because you guys were shown how to derive those formulas yesterday. But if there's any question, just these are simultaneous equations. That's pretty much straightforward. So we go to part E. What's D primary line constants? Then you have the voltage. Is it called the voltage coefficient? Deflection coefficient, gamma L. So what I need you to note about this voltage coefficient thing. Sorry. What I need you to note about this is that when it's big L, just know that's when the distance L, the distance on that transmission line, the distance between it's when L is equal to 0. Munaelewa? When the distance, how do I explain this, that distance thing? Tuseme si iko hivi, si ndio? So this is the source, and mnanisikia?
Yes.
Okay, so this is the source. Now, this is
Yeah,
where the load.
tunasikia.
This is where the nini is. Okay, why am I giving load is? Yeah, this is such a wrong letter for this. But just take for this is the load. This is where the load is. And this is the source. So the voltage, everything incident is going this way. But then now, please correct me if I'm wrong, if I didn't understand it well. But this here, this distance here, this one here, we are starting to look at it from this side now. Sawa. So this distance, we are going this way. So like that. So when this distance L from the load side is equal to 0, that's when we call it gamma L. But if that thing L or any equation you find in transmission line, this big L just shows when L is equal to 0. But this small l, it means it's at any point on this line. It can be here, it can be here, it can be here, it can be here, but it cannot be when L is equal to 0. So this gamma L, okay, yeah, yes. So we are looking at it when this distance here is equals to 0. When L is equals to 0. Okay, I hope mumeelewa that part. So it's equals to VR over V. The reflected voltage divided by the incident voltage. So that's when you derive that, all these equations, that's page. From page 82 to page 84, all these equations to do with voltage, meaning that. So that's something you can read on your own, but we're just showing how to tackle the question. So the gamma L is equals to, we were given ZL. Remember, we were given before the ZL here. The ZL is 115 minus J 75 ohms. So when you input that and you input your characteristic impedance, you get your gamma L as that. Tuko sawa sawa hapo? Haya. Okay. Voltage standing wave ratio is equals to V max divided by V minimum. So you'll come and say V max when you do this derivation. We know that V max is equals to VI plus VR, the magnitude. That's V max. And V in is equals to V incident minus the reflected. So when you substitute this, and you also substitute those formulas for gamma, where you know gamma L is equals to VR over V incident, you'll be able to find this formula, this one here. So when you do that, you get the voltage standing wave ratio is that. Okay. Now remember, I told you guys about the small l. So when you asked, okay, so now question G was asking us about what? It was asking us about, we are now at input impedance. So input impedance is just the input at the, like from the source. So like on that line, the input impedance, just from on 7Z. So it's at any point in that line. So that's why we denoted it as Z small l, which is equals to the characteristic impedance times 1 plus gamma L over 1 minus gamma L. As yes. Please note that this is small l. Yeah, please, or this is small l, this is small l, because you're looking for the input impedance at any point in the line. Then when you do that, we also know that VR, it's so, anyway, these formulas are so many, but let me tell you, these formulas, thank God it's just open book, so you can access them. I'll give you guys the pages and everything. So VR over VI. So this small r and small I, it means, is because you'll find that denoting capital letters and small letters. So you need to keep noting that the capital R and small capital letters show when the L is equals to 0, and small r and small I just show, small letters just show at any point in the line. Okay, so when you do that, when you just substitute the values, we found the beta and we know phi. Phi is from this gamma L here. This phi here is from here. Sawa. So you just convert this to radians, then you input it there. If there's a question, just say. Then when you do that, you'll find you just input all these things in the calculator, then you will find your ZL as that. Okay. So now what else? Input impedance. Okay. So now input current. When you asked for the input current, you just take the VRMS value, and they said it's the source voltage is 100. They said the source voltage is 100 VRMS. So you'll just come and say 100 divided by the Z small l at any point, the input impedance at any point. Then you'll find your input current RMS is that. Now receiving end voltage is when L is equals to 0, as I have just said. So VL, so it's V sub capital L. So that's equal to V incident voltage plus reflected voltage. Then you get that. Then also now the input voltage, you will derive it from the formula. As I said, all these formulas are there. This formula, this one is important. That's where we got the VI from. So you make VI the subject of the formula, since you know beta and you know L, and we know our input voltage as 100. So that one you can do. Then gamma L. Then you have input voltage, right? At when L is equals to 0. So now you have to find V capital VR, and you can, the only one, and we found gamma L, right? Yes. So and you have VI, so you're going to just substitute that back, and you'll be able to find your VR. Then you'll say V reflected voltage plus incident voltage is equals to now the voltage at when L is equals to 0, the receiving end voltage. So receiving end current, it's just pretty much the same. You just say VI minus VR divided by the characteristic impedance. Then you will get it there. And then we have the receiving end power. Please note that receiving end power is not the same as reflected power at the load. Receiving end power is, you'll say VL. We found VL here before, yes? We found this is VL, right? And then you'll also come and multiply it with this current that we found. Then you find receiving end power. Reflected power at the load. Please, we know that the reflected power is directly proportional to the voltage reflection coefficient, the magnitude of that squared. So, but you're looking for, so you'll come and say the receiving end power times this is the magnitude, times the magnitude squared. Then you get your reflected power. Yes. So I think I'm done.
Oh, thank you, Gisheru and Fiona. So Nigel, the floor is yours.
All right. Topic 1. Acha ni present screen yangu. Somebody say a yes kama anaona screen yangu.
Yes.
Okay. I'll call question 5, page 186. It's majorly topic 1. A, define a reciprocal network, symmetrical network, and a balanced network. So, kwa notes zangu, okay, zenye nimeandika, I've answered the questions, and also I was writing some short notes kidogo. So, I think follow this pen of mine, ndio usipotee tafadhali. Alafu kama mtu ako na swali, apige tu kelele. Aya. A symmetrical network. Oh, sorry. It's supposed to be a reciprocal network. Oh, okay. So, a reciprocal network is a network that is made up of only linear bilateral passive elements, and the transfer impedances are equal, i.e., Z12 is equals to Z21. In brackets, it has no dependent sources. So a linear element is just like they include capacitors, resistors, and inductors. Nonlinear elements, they exhibit linear relationships with current and voltages, like Ohm's law, V is equals to IR for resistor. But now nonlinear elements ni kama kina transistors, diodes. So hizo haziko kwa reciprocal network. Bilateral just means that they can pass currents on both sides, both directions. Alafu passive elements, they are passive elements. Okay, opposite of passive elements, yeah. Active elements, more active sources, voltage sources, and current sources. And the transfer impedances are equal to Z12 and Z21. So any Z parameters, I took the liberty kuchora two-port network hapa. And here, V1, V2, current of I1, port 1 goes in, I2, and port 2 goes to the other side. Now for Z parameters, also known as open circuit impedance characteristics. And the parent equations there is in A. So V1 is equals to Z11 I1 and plus Z12 I2. That's equation 1, and V2 is equals to Z21 I1 plus Z22 I2. So Z11 is just V1 over I1. Yeah. Z11 unachukua V1 and let I1 huku. Because you are looking into from port 1 into the circuit, I2 is 0. It is open circuit. So this is the formula. Alafu inaitwa open circuit input impedance, also known as driving point impedance. Kama nakumbuka last sem, Professor Uma alikuwa anauliza maswali zingine zenye zilikuwa zinahusu driving point impedance. So going on, Z12 is equals to V1 over I2, which I1 is equals to 0, meaning port 1 is like itakuwa open circuit. So tunaangalia circuit from this other side. Also Z21 is equals to V2 over I1, where I2 is 0. Tunaangalia from this other side tena. Hizi mbili zinaitwa transfer impedances, nimeandika hapa. Alafu Z22 is V2 over I2. So V2 over current I2 vile inaingilia hii side. I1 itakuwa 0 because this other side itakuwa open circuited, and that is known as open circuit output impedance. So for a reciprocal network, which is a network that is made of linear bilateral passive elements, Z12 is equals to Z21. Just simple like that. To the less symmetrical network, it's also a network made of only linear passive elements, and the open circuit output impedance is equals to open circuit input impedance. So the difference between the symmetrical network and reciprocal network, reciprocal network, Z12 is equals to Z21. The transfer impedances are equal. That's the major difference. And then a symmetrical network, Z11 is equals to Z22. The output open circuit output impedance is equal to the open circuit input impedance. So some short notes over here. Symmetrical network is characterized by its characteristic impedance Z0, yomona mara mingi, and its propagation function is where V1 over V2 is equals to exponential the propagation function. So this is just the definition of characteristic impedance. Ukipitia kitu baadaye, you'll just read it. It's not in the question, but just to know. Balanced network. So in a balanced network, I listed the networks that we have that we have in topic 1, mostly T networks, pi network, lattice network, bridge network. These are networks sasa, they are unbalanced networks. So to balance them, okay, let's go back to the definition. To balance them, a balanced network is a network in which the corresponding series impedance elements are identical, and one in which these elements are symmetrical with respect to the ground potential. So like later on, a lattice network can become a balanced network. I didn't actually find an easy explanation to this. Nilipata kwa dissertation fulani hata, nilikosa kwa vitabu. But there was an example about it, like using audio, balanced audio. It uses 3 conductors to carry the audio signal. 2 of the conductors carry the negative and positive signal, AC of course, and the 3rd one is used for grounding. Ukiangalia like auxiliary cables, some earphones zenu, mostly zinakongana. 3, like you can see 3 markings on them that depicts the 3 conductors, but unbalanced signal flowing in an unbalanced circuit, I guess. There are only 2 conductors. One carries the positive and the other one the negative, and is also for the ground. So you find that this unbalanced signal, there's some earphones zenye ni bonoko. Okay. Zinakongana 2 markings, the positive and the negative one. So ISO mostly who transmit an unbalanced signal. The isolated ground makes it cleaner, makes the audio to become cleaner compared to the audio that is flowing in an unbalanced network. Yeah, but you can find more balanced networks, I guess, on internet, on my YouTube, but this is all I found. So, any question A? Anybody has a question? How to Ndela? Oh, okay. No one. Yep. Tuendele?
Yes, tuendelee.
No. Okay, okay. Question B. design and sketch the circuit for a symmetrical T-type attenuator with a characteristic resistance of 800 ohms and an attenuation of 2.71 NEPA. Okay, this is it. So I'll take you guys on a little detour. Attenuators, it's an application of a two-port network. So its definition, it's the two-port network that reduces predetermined amounts of voltage and current or power between its properly terminated inputs and output ports. So like, just from the name attenuator, kwa English, attenuate inamaanisha kureduce. So it reduces the voltages, current, and power depending on how it's terminated inside a circuit, and it only uses resistors. So attenuation, normally N, is the output. N is only used in power when you've been given power or when lattice network. Okay. Lattice. Okay. Most attenuators use lattice networks. So nikamua nikuja niwaambie kuhusu lattice networks. Nilipitia kidogo. So this is what I got. It forms bases of two-port networks such as attenuators, filters, phase changers. Is how it looks like. There's supposed to be an arrow. I1 going into Z1, ZB, then this is the output ports, input port, V1, V2, I2, ZA is supposed to be ZB. Yeah, there's a lattice network. It's equivalent to a bridged network is this, where I1 is here, I2 ndio hii hapa, ndio hizi output points zenyewe, alafu be careful, positive iko hapa, negative iko hapa. Signage is important, mtaona tukiendelea. Positive, negative. So analysis of it, this is the bridged network. It's just the equivalent lattice network. So when I1, okay, let me use the Z parameters over here to get the formulas for attenuation yenye iko huku chini. V1 is equal to Z11 I1, Z12 I2. V2 is that. Those are the parent equations for Z parameters. So Z11 is V1 over I1, whereby I2 is equals to 0. So tunakuja hapa. Consider this first KVL loop, whereby I1 flows, then KCL upper in a split, but consider this loop peke yake, whereby I2 is 0 now. So V1 is equals to I1 over 2 here. I1 over 2 will pass through ZB, and it will pass through ZA, na itakuja itoke huku. So I1 over 2 multiplied by ZB plus ZA is equals to V1. Or you can also write that 0 is equals to 0 is equals to this. Okay, let me just put this as X. So X plus minus V1. poleni siju kuchora vizuri na mouse, lakini this is technically it. It's just the same as this. So V11, sorry, is this. So Z11, which is V1 over I1, becomes ZB plus ZA over 2. Now coming to Z21, we'll solve for this. So tunakuja hapa. When I2 is 0, now this part yote is 0. V1, tunaangalia now this loop here katikati hapa. So I1 itakuja iflow huku, itakuja iflow hivi, but tuna consider from this positive side ikienda to this other side. So V2 now, this V2 is equals to the total sum of voltage drops inside this loop, which is because we are going against I1 over 2, itakuwa negative I1 over 2 times ZA, but ikikuja hivi inaenda along with I1 over 2, which is I1 over 2 times ZB. So kileta hii hapa down inakuja to I1 over 2, which is ZB minus ZA. So V2 over V1 becomes ZB minus ZA over 2. Now we go to whereby I1 is 0. Or anybody akona swali kuhusu hiyo part?
Oh, no question.
Okay, right, nice. All right. When I1 is 0, when I1 is 0 now, must consider here. I used this diagram now. From the parent equations of Z parameters, now this one will be 0, zote zitakuwa to 0. So V1 itakuwa Z12 I2, V2 itakuwa Z22 I1.
Oh,
So Z1, 2.
Nigel,
Okay.
there's a
Yeah.
question. Why are there two ZAs and ZBs?
Why are they two ZAs and ZBs? These on here. Niangalia nimeuliza.
Yeah.
Oh, Mike. Okay. They come from this lattice network yenye nilionyesha before. This one, a lattice network, an attenuator mostly it's made up of it can be made from a lattice network, and lattice network in attenuators are reciprocal. So ZA, these are the series arm impedances, E, ZN, and ZB, and the diagonal impedances. They are diagonal arm impedances. So ZA, wait, oh, you meant these. Oh,
Yes,
nimekuelewa,
this one.
nimekuelewa. Okay, sikuwa nimeona actually. Poleni. It's just a typo. Yeah, I guess. Yeah, it's supposed to be like that. Thank you, Mike. Aya, tukiendelea. I1 is equals to 0. So this is supposed to be ZB. Yeah. V1 over I2. So the Z12 now. V1 over I2, whereby I1 is 0. We consider current, this I2 now, because this is V2. I2 will flow his side, and it will come and split into two, this side and this side. This one will become I2 over 2, and this one will become I2 over 2, and you're gonna flow to the other side. So I considered the first loop, I considered this outer one, whereby V1, this loop, V1, because we still have V1 over here, is equals to negative I2, because we're going against this current, ZA plus ZB, I2 over 2. So that forms the KVL equation for Z12, whereby, okay, simplify, it becomes V1 over I2 is equals to ZB minus ZA over 2. And if you've noticed, Z1, 2, this one is equals to Z21. So our network is symmetrical. Let's see if it's also reciprocal. Z22 is equals to V2 over I2, whereby I1 is 0. I consider this loop over here, E and I. So I2 flows inakuja hapa inakuwa I2 over 2, ita flow tena hii side ingine. So I2 over 2 times ZB plus I2 over 2 times ZA, because ita flow hivi na ikuja hivi, just this loop peke yake. So I found V2 over I2, which is Z22, to be a half ZB plus ZA, which of which Z22 is now equal to our Z11. So you can see that our lattice network is reciprocal and symmetrical at the same time. So to get the equations of we're supposed to look for to get ZA and ZB separately now, because now they're engraved in this, they're included in this Z22 and Z11, Z21, and Z22, Z12, sorry. So to disentangle them from there, we add Z11 plus Z12, which is Z11 plus Z12. Z11 is a half ZB plus ZA plus Z12 half ZB minus ZA. So ndio hii hapa by half ZA itaenda na half ZA, so tabaki na half ZB plus half ZB, whereby Z11 plus Z12 is equals to ZB. So to get ZA now, we subtract Z12 from Z11. So a half ZB plus ZA minus a half ZB minus a half ZA. Is to cancel, then itakuwa half ZA minus half ZA. So Z11 minus Z12 itakuwa ZA. So we have ZA and ZB now. With this now we can create an equivalent lattice network if we have a symmetrical reciprocal network, because we've just seen that from easy derivations we get a symmetrical reciprocal network. Tukiendelea, from Zn na Zb, we can get the characteristic impedance of the lattice network, which is ZOL into a square root of Z11 squared minus Z12. This is a formula kwa kitabu. So it's an identity whereby Z11 squared minus Z12 is equals to this identity per math. Then this one is equals to ZA and this one is equals to ZB. So our characteristic impedance is root of ZA times ZB. From there, propagation coefficient, this whole one, is the formula for propagation constant or coefficient. Yeah, that's something. It's from the book. Ln of 1 plus Z11 minus Z12 over Z11 plus Z12 over this minus this. But now if you noticed, I said before that to get attenuation in Nepers, you take ln of n, you get n in Nepers. So this is ln, and now this is the value of n. So we can see that this is it's just the same as our attenuation in Nepers. It's the same thing. Taiwan umbrella. So this one I replaced with ZA and ZB, and I got to this. And of course, if you simplify it, it'll be in the form of this plus JB. With that information, tunaweza rudi kwa lattice attenuator yetu sasa. Ndio. Lattice attenuator network may be converted into an equivalent T, pi, or bridge T resistance network using bisection theorem. Sorry. Hiyo ni Bartlett's bisection theorem, but here hatutaitumia. Here it just flows in directly. We don't need to use it, you'll see it. So we consider the lattice attenuator below. This is an example of a lattice attenuator, but an attenuators only use resistors, so they're purely resistive. So in our case here, the zenye tumekuwa tukiderive with impedances Z, we change it to just R because they're purely resistive. Our characteristic impedance, looking into the circuit from this side, it's given by ROL, which is equals to root of RA, RB. So we are to derive the equations that we're supposed to use in this question B. Oh, I've got 9 minutes. Okay. 1 plus RA over RB over 1 minus RA over RB from here is equals to propagation coefficient, which I told you guys is equals to now N. Because the circuit is not purely resistive, there is no phase shift now, and it's independent of frequency, so it's just purely resistive. So N is equals to 1 plus RA over RB. If you follow it through, we come to here. ROL is equals to root RA RB. Then we do some math over here. If you can follow, RA RB is equals to ROL squared. RB is equals to ROL squared over RA. We substitute now this into equation 1 here. So we substitute RB hapa, so itakuwa root of RA over RB, of which RB ni hapa. So RA divide by RB, I did it hapa chini, inakuja to this RA squared over ROL squared, so itakuwa this. So this equation boils down to just this. So tukiendelea, N, which is attenuation, is equals to RO plus RA over RO minus RA. So simplification, cross multiplication, it's a simple thing, 2-minute thing, less than 2 minutes. It'll lead to this. So this equation is important. The same thing we do for RB, the same principle, whereby ROL is equals to root of RA RB, ROL squared is equals to RA RB. Then simplification, cross multiplication, utapata equation, sorry, C equation, hapa. So these two equations are important in simplification of our answer. So back to our question, isn't just a few short notes of what I've explained hapa juu, naweza pitia baadaye. So our question, type attenuator with characteristic resistance ROL 800 and attenuation of 2.71 NEPA. So ROL is this, attenuation is 15.03. I converted it because ln of n is equals to n NEPA. So n, nikapata 15.03. So substituting this to get RA, it's from this formula that I told you guys was important. You just replace RO and N, then you get 700 ohms. Then for RB, you use this formula now to get 914.04. So we're supposed to create we're supposed to put it in a symmetrical T-type attenuator. So Rn and Rb, basically their values from a lattice network. So to convert them to you can use Bartlett's, but here we don't. Here we don't use Bartlett's. There are these formulas. Iko kwa kitabu ZA, which is equals to RA that we found, is equals to Z1. These are T-type network. This is Z1 also because it's a reciprocal symmetrical network. Alafu E is Z2. So ZB minus ZA times a half is equals to Z2. So it's just simple like that. So Z1 ni 700, EPR 700, I love Z2 and 7.02. So yeah, end of question B. Does anyone have a question, Apple? So basically, it's really the long nini yenye nimetumia ni just derivations, but the part that you need ni hapa. Hapa tu, hapa tu. Hapa, peke yake. Kuna mtu akona swali?
Nigel,
Yes.
could you please go back to the your page? This part you're saying you're talking about. Okay, when we're changing it, when we're able scroll chini kidogo, yeah. When you're changing it to a T network,
Yeah.
we read the method you just used.
Okay. Kuna hizi formulas kwa book. There's a derivation, but I don't think there's a derive sign any time. But it's just a formula from because from a lattice network kuna ZA na kuna ZB, asymmetrical reciprocal lattice network. Na in our case it's an attenuator, ni RA na RB, si ndio?
Yeah. Nimeona.
So,
Nimeona.
no.
I've seen, yeah.
Okay.
Thanks.
Okay. Good. All right, to delay. Question C. What does it say? Derive expressions for the transmission parameters in terms of short circuit admittance parameters. Okay. So transmission parameters, it's just ABCD parameters. In terms of short circuit admittance parameters, is on Y parameters. So lazima ujue ABCD parameters na Y parameters. Niliziandika hapa. So these are the parent equations. It looks like a tree. These are the parent equations for ABCD parameters, whereby V1 is equals to AV2 minus BI2. I1 is equals to CV2 minus DI2. So for A, it's just like the way we did for Z parameters, V1 over V2, whereby I2 is 0. Now, you can notice it's input voltage over output voltage. That's just reverse voltage gain. And B, itakuwa B, because here itakuwa, because V2 will be 0 now, itakuwa V1 over negative I2 is equals to B. This is a short circuit transfer impedance. And then for C, now this one, I2 itakuwa 0, so here itakuwa I1 over V2 is equals to C, whereby I2 is 0 now. This is open circuit transfer impedance. Now, alafu D, it's I1, itakuwa 0, because itakuwa 0, itakuwa I1 over I2. There is a negative sign over here. Oh, yeah, it's common here. So D itakuwa I1 over negative I2, whereby V2 now will be equal to 0. V2 itakuwa 0 hapa. Oi, nimeandika nini hapa? You can just mnaweza pata the concept. This is short circuit reverse current gain because it's input current over output current. Now we're supposed to put them in terms of Y parameters, ndio? So these are the parent equations for Y parameters. Hizi parent equations mzishike ama mweke ma sticky note kwa ukuta kwenye mtafanyia teo. I1 is equals to Y1 1V1 plus Y1 2V2. This equation supposed to be equation 1. Chana na imambo. I2 is equals to Y2 1V1 plus Y2 2V2. That's the second equation now. So to determine the ABCD parameters in terms of Y parameters, we set I2 to 0 from this second equation now. So I1 is this, but I2, we set it to 0. So using the second equation that we've set I2 to 0, we can just take this equation to this other side such that you call Y2 V1 minus Y2 V2. So V1, if we substitute up itakuwa V1 over V2, which is equals to negative Y22 over Y21. But now this V1 over V2, it's A. And now tuko na value yetu ya A in terms of Y parameters, which is this. You can try out for Z parameters. You'll find that itakuwa equal to E. Tukiendelea for C now. C now it's a little bit longer kidogo tu. Lakini we substitute, we make V1 subject and substitute it in this equation, this first equation. 1.27. You'll just use these numbers hata kama zi make sense. In 1.27, this one, whereby V1 now will be equal, it's just the same as, and in this equation now, tunaendelea nayo sasa. Like V1 is equal to negative y22 V2 over y21. It will be this now. So we make V1 subject and substitute in here. Tutapata I1 for this first equation now is equals to y2. Tumesubstitute na hapa plus y12 V2. Alafu tukiendelea, just math. Multiply everything by y21, this side disappear, alafu ibaki I1 y21 is equals to negative y22 y11 v2 plus y11 y12 y21 v2. This now. So if you factor out v2, you notice that there is y22 y11 minus y12 y21. And kikumbuka kwa matrices, this is just the determinant of y. I wrote it down here because y22 times y11 minus y21 times y1 minus y21 times y12. It's here. So this just boils down to this, whereby I1 now over V2 is equals to this delta y over delta y21. So tukinotice hii I1 over V2 yenye tumepata ndio hii hapa. So it gives us the value of C. So tuko na A na tuko na C. So tuendelea, tunatafuta B na D. Now for B and D, we set V2 to 0 from these parent equations now. So this one, sorry. So hii zitakuwa 0, tabaki na hii na hii. Whereby ndio hii hapa. So B is equals to, we take V1 over I1. V1 over, sorry. This one, this second one, sorry, si ya kwanza. I2 is equals to y21 V1, whereby tutapata hii, saa tuna equate, itakuwa V1 over I2, alafu tukipeleka the other side itakuwa negative. So B itakuwa negative V1 over V2. So whereby V1 over I2 will be equal to 1 over I1, 1 over Y. Wait. Back up kidogo. Okay. I1 is equals to Y11 V1 and I2 is equals to Y21 V1. So for B is equals to negative V1 over I2 because tumepeleka Y21 hii side ingine na I2 tumeipeleka hii side ingine. So inakuwa V1 over I2. Whereby V2 is 0. It's 0 hapa. So B tukinotice hapa tumepata tu ni V1 over I2. But tukinotice from hapa B inakuwa V1 over negative I2. But sasa hapa hatujapata negative. It was just V1 over I2. So we introduce the negative to this one and we introduce the negative to the Y21 that was remaining up. So inakuwa 1 over minus 1 over minus Y21, which is in terms of Y parameters. Mnaweza fanya for Z parameters, it will be equal to that. So for D, which will be negative I1 over I2. There's something wrong over here. Just a minute. This is I1 over I2. We do this. We take this equation, the first equation, over the second equation because it's I1 over I2. Remember, mkianza kuandika, you can write just this ndo ikuguide such that hapa sasa tunakuja tu virahisi tunasema tunachukua equation over equation. That's that v1 and v1 zina cancel, but now we don't negative over here. So because in the equation, huko parent equation imekuwa introduced, we'll also introduce hapa in the y11 over y21, and that gives us the y parameters in terms of transmission parameters. Yeah, I guess vice versa. Yeah. So we're done with question C. Anybody has a question on that? 6 minutes past time. Kuna mtu akona swali ama tuendelee? Okay. But it's simple stuff, like ni kitu yenye unakaa chini in less than an hour, ukipitia tu ni rahisi, but sticky notes pia zitakusaidia. Tuendelee. Part D. Consider the network of figure Q5 operating at 100 radians per second. This is a frequency. Convert it into an equivalent pi network. Obtain its short circuit admittance parameters, again Y parameters. Determine its image impedances when appropriately terminated. Tunaanza na ya kwanza. Convert it into an equivalent pi network. So this is the overall network. What I did, this is a T network. I converted it into a pi network. Then after converting it into a pi network, una notice kuna e 5 millifarad itabaki hapa chini. Hapa kadogo. Yeah, here. So I then took a parallel of this and converted it into one element, which gives a pi network. So doing it, there's these formulas from the star delta conversion of T network to pi network and vice versa. It's over here. This is a T network, pi network. There is star delta. Uzuri cut e-exam ni open book by there, so you don't have to cram these things or take a long time to internalize. So this is the input network, input port, this is the output port. V2, and this side V1. So to get ZA, let me zoom in. Get ZA, itakuwa Z1 times Z2 plus Z1 times Z3 plus Z2 times Z3. It's just alternate. If you can look at it in the book, but there is a pattern. If you just see this first one, if you just understand this first one, is again, of course, ni simple. There is a pattern. Alafu to get Z1, Z2, and Z3 from pi to T network conversion, it's just ZA, ZB for Z1 over ZA plus ZB plus ZC using this star delta. If you just internalize, I don't want to explain it now because time inaishia. You can just look at it. Tops 2 minutes. Utakuwa ushaona pattern. You now are supposed to convert T network into a pi network. So tunatumia hii ZA is equals to this, ZB is equals to this, ZC is equals to this. Now, this is my Z1, this is my Z2, this is my Z3. This resistor now, this resistor is Z2, this one is Z1. You can notice that this one it's not a reciprocal network because this one Z1 is not equal to Z2. Or is it symmetrical? Okay, either you can look it up. But here it doesn't matter. So ZA is equals to Z12 here. So it's the impedances. So J omega, which is 100 times 40 millihenry upper times 1, which is Z2. I just filled them out, changed this one into an impedance, into an impedance, into an impedance. Nikazifill hapa. We calculate kwa calculator. Okay, input kwa calculator, it gives you this. So this is your value for ZA. We have a ZA now, where we can convert it into a pi network. ZB, the same thing, because the numerators are the same, which is 2 plus J12, sorry, ohms. ZB is equals to this. Nikapata hiyo. ZC, just did the same process. Nikapata hiyo. This question, by the way, when you're told to convert, you just, if you know the process of the process you're taking, you explain here, which led to this. The rest, it's just calculation. So the calculation too. It's nothing hard. So upper kwa brackets niliandika like 1 plus J6, it's like 1 resistor and the inductor of 0.06 henries. I noticed in one of these exams, answers zenye alipeana nyuma, you just don't write 1 plus J6, you categorize them. Like a resistor of this and an inductor of this, a resistor of this and an inductor of this. Pretty simple. So later on nikapata ZA, ZB na ZC nishazipata, which is here now. But remember, there's that rogue capacitor over here. Now to combine it here, ZC in parallel with 5 microfarad. I took the parallel A times B over A plus B. So this times this, I noticed there's a mistake because it's a capacitor. Supposed to do 1 over that, same to the denominator. If I go 1 over that. Alafu inakupatia the new ZC now, where we can input it hapa, but it's not this now. You'll calculate it, then you'll find your own value, which gives an equivalent pi network. So to convert. Anybody has a question there? Yeah. We continue. Hello. Okay.
Yes, we can continue.
Thank you, Celeste. Thank you, Celeste. Okay. Supposed to obtain its short circuit admittance parameters. Short circuit admittance parameters. Uzuri tumezifanya huko juu. As you can see, this apparent equations of admittance parameters, and there is these three formulas or 3 equivalents of three equations that will help you, because now we have ZA, ZB, and ZC from hapa. You can convert them to admittances, reciprocal of impedances. So to get YA, YB, and YC. So there's this formula also from Y parameters and conversion of lattice networks to T network or pi network in terms of Y parameters or Z parameters. There is this formula whereby Y11 is equals to YA plus YB, Y22 is equals to YB plus YC. The derivations of this formula, which I won't get into now, ziko kwa kitabu. It's pretty straightforward. Y21 is equals to negative YB, and Y12 is equals to negative YB. Negative YB. With these equations, tunaweza pata our short circuit admittance parameters, because we have YA and YB, and we have YB and YC, and these are the values. So nilizichukua tu hapa nika input hapa na nikapata Y parameters zangu. So nikapata max zangu. So ni hiyo. That's the answer to 2. 3 now. Determine its image impedances when appropriately terminated. Image impedances. Image impedances, there are 2 subtopics, sorry. Kuna image impedances na kuna iterative impedances. So image impedances, this one, it's like when you connect a 2-port network, hii hapa juu, hii diagram yangu yenye niko nayo, hii hapa, to another 2-port network, whereby the output of this one, let me just draw. Forget the background, tachora tu over it. This is another 2-port network, like this. The input of the next nene, it's the output 2, then 2 like this. Then this side will be 1 now, the input side. Sorry. 1, alafu itakuwa 1. So we just do it like that. Then the next nini, that is image impedances. Itakuwa 1, alafu 1, alafu side ingine itakuwa 2, 2, just same pattern, same pattern, same pattern. That is any image impedances. Now for iterative impedance, it's the opposite. The output of this will go to the input of the next two-port network, and the output of the next two-port network will go to the input of the next two-port network. That's the difference between iterative and image impedance. Back to our question. Image impedance. There's these two formulas. There's a whole 2-page derivation of these two formulas. I haven't seen a question where he has asked you to derive these two, but just PTI it and ikuwe kwa mkono yako during exam such that you can pass it through it anytime. Zi1 is equals to AB over CD, root of AB over CD, and Zi2 is equals to root of BD over CA. These are transmission parameters. So from this, we have our Y parameters, and we're supposed to convert them to transmission parameters. And then from the transmission parameters, we get our image impedances, the A, B. We get the image impedances, the Zi1 and the Zi2. So it's simple enough because before ulikuwa ushafanya ndio easy in terms of admittances, ndio easy. C ndio hii hapa, A ndio hii hapa. So you just plug it in over here, whereby A is this, and you have your Y22 ndio hii hapa, and Y21 ulipata huku juu, same thing, so you get your A. Same thing to B, get your B. Same thing to C, delta Y, is this, the determinant of the matrix, get this. And same thing to D, get this, whereby it will give you an answer. Now, on to units for ABCD parameters. Not for A and D, they are dimensionless, because if you notice, this is just admittance over admittance, whereby the Siemens will cancel. So itakuwa dimensionless. Sorry. Same thing to D. Itakuwa Siemens zenyewe zita cancel. But now for B and C, B, because it's 1 over Y21, this is just the same as impedance. It will be in terms of ohms now. But for C now, because it's determinant, this is just the same as Y squared minus Y squared over Y. You'll get okay, it's the same as Siemens squared over Siemens, whereby the answer will just give you Siemens. So C has units of admittance, B impedance, D and A are dimensionless. So that's part 3 of D. Does anyone have a question? Anyone have a question? What wrong with beats there? Okay. Naongea peke yangu sasa. Hello?
No, I think your presentation was pretty much comprehensive and straightforward.
Okay.
So yeah, it was a good one.
Sawa basi. Okay, the only part yenye sijapitia ni Bartlett's bisection theorem, filters, H and G set parameters, na interconnection of 2 4-terminal networks na unsymmetrical networks. Hiyo ukiona like 5 hours ama 6 hours utakuwa ushamaliza section A. Topic 1, sorry. Alafu uzuri ACT, it's the last exam, so you guys got time.
Okay, thank you so much, Nigel.
Karibuni.
Okay, so I'm going to stop recording.